So here we are with Professor, and today we're going to talk about special relativity. And you got your whiskers caught in your tie, buddy. All right, we're going to talk about special relativity, how it relates to time dilation. This stuff may sound complicated, but we're going to simplify it as much as possible. And Professor, being the professor, is an expert at this. I'm a little rusty. It's been a while since I thought about this stuff, but Professor's going to help me out here. We're going to start by just thinking about a few things. Let's just think about what happens if we're on the ground observing something go by. Let's call it a train. And it goes by at a certain speed. Let's say it's 100 miles an hour. Okay, it goes by 100 miles an hour. And let's say that the person on the train switches the light on the train, and it lights up things in front of the train. No problem. We see that. We even see what it lit up. People inside the train or on the train, they're traveling 100 miles an hour, the light goes on, things light up in front of them. No problem. We're both pretty much having the same experience, the people on the train as well as the people on the ground, right? So let's just change it a little bit and let's pretend that the train is now, say, going half the speed of light. Pretty fast, right? But let's stay with us for a minute. It's going at half the speed of light. Now, the person running the train switches on the train's light. And what happens? The light goes out from the train at a certain rate, and the people on the ground see this going out at a certain rate, and the people on the train see the light going out at a certain velocity also. Right? Obviously. Okay. Nothing special here so far, right? Except for this. How fast would we see the light going forward from the train as we're observing from the ground? Well, probably the speed of light, because it is the speed of light. But what about the train, though, going half the speed of light? Shouldn't it add on to the speed that we're seeing it? So train's going at half the speed of light. We're watching the light on the train go on. Shouldn't we on the ground observe that light, Professor, going forward at 1.5 times the speed of light? No. Observations, not with trains, but with other methods, have shown that it's constant. It's always going to travel at the speed of light, regardless of where we are observing it from, regardless of the observer. Light travels at the speed of light always. Interesting. So, we're watching the train go by. The person turns on the light on the train. We're watching the light go at the speed of light. So, in our mind, then we're thinking, well, relative to the train, a person observing it on the train must see this light go forward at half the speed of light, shouldn't they? Because they're already traveling at half the speed of light. If they saw it going half the speed of light also, it would match our observations from the ground, right? Interestingly, observations have shown that when the person on the train, if they were to turn on the light, they would observe it going away from them at the speed of light. How is that possible? Well, you might say, well, the speed of light is always the speed of light, so of course they're going to observe it at the speed of light. They turn on the light, is going forward at the speed of light. Yes, but they're also traveling at half the speed of light, so the person on the ground should be seeing this go by at 1.5 times the speed of light. I know you're getting bored because it's so easy for you, but they don't know yet. They don't have your experience in physics. So, how do we rationalize this? How can we rationalize these two different experiences and make it so it's right for both observers? How could we possibly do this? Let's think of it this way. What if, for the person on the train, what if time slowed down for them to allow the light to catch up to the speed of light? The faster we go, the closer we get to the speed of light, the more time slows down for us. Whereas another observer from the outside, time goes on as it would. Here we are, we experience time the way we experience it. But when we get closer to the speed of light, time slows down for us. we won't notice it. Things will seem as if they're going on the way they normally would. Special relativity deals with motion, and especially with motion that starts to get to enough of a percentage of the speed of light that it starts affecting our experiences, and especially time, our experience of the passage of time, time itself. So what is the bottom line? Here's the earth-shattering revelation with this. Time is not the unchanging constant for everybody. Time is relative. The speed of light is unchanging, and time has to change as far as the perception of it based on the observer to accommodate for that. So the passage of time is not a constant. The speed of light is a constant. Interesting, very counterintuitive based on our experience. You would think it would be the other way around. You would think the speed of light, would be what would change. No, the speed of light is a constant. It's time that has to change as far as our perception of it and the passage of it to allow the experience of the person on the train to be valid as far as thinking that light moves away from the train at the speed of light, and the person on the ground thinking the same thing, that light moves away from the train at the speed of light. So time changes, the perception of time, the passage of time. So the person on the train, the bottom line is they experience time differently than the person on the ground. Interestingly, the closer we get to the speed of light, the more and more and more time slows down. So when we get near the speed of light, time is almost stopped. If we were able to achieve the speed of light, time would have stopped for us. There's reasons that Einstein would say that a massive object, an object with mass, can't reach the speed of light. Totally different topic. Maybe we'll discuss it with Professor at some other point. But for now, we're going to keep things as simple as possible, we said. Right? But even this is a mind-boggling thing to think if you've never thought of this before. So again, please stay with me just for a little bit longer. Okay, so we get closer to the speed of light, time slows down for us. You're thinking balderdash. Is that valid? Is that valid, Professor? Balderdash? Okay, you're thinking no way. But you know what? This has actually been experimentally proven. It's been experimentally proven in many ways. It's been experimentally proven in a lab using subatomic particles. It's been experimentally proven using electromagnetic waves and signals that we might bounce off satellites for GPS navigation. We have to make corrections for these relativistic changes once these things start getting close to the speed of light, which, by the way, signals getting bounced back and forth from satellites are pretty much at the speed of light. And there are changes based on how far the satellite is, from the Earth and how quickly it's traveling around the Earth that will influence that. There's another thing that influences our perception of time and time itself, but we're not going to get into that right now. It's gravity, by the way, but we're not going to talk about that right now. So this is a way into the future. So is time travel possible? Yeah, at least into the future. Is time travel possible in the past? Maybe, but that might be a future video. Right, Professor? Einstein, boy. Who doesn't love Einstein? Right. Yeah, that's a joke for the physics community, right? That's pretty good, buddy. All right. So until next time, thanks for watching. Hopefully you've learned something and had maybe some appreciation for Einstein. If you're interested in more about this, there's a book that I'd read in the past, which I haven't found online as far as the exact same edition, but it seemed that they've updated it. It seems to be the same book, but it's called something a little different than what it was in the past. And what it seems to be called now is the Special and General Theory of Relativity, or the Theory of Relativity, the Special and General Theory by Einstein, by Albert Einstein. I'll put a link in the description if anybody's interested to get it off Amazon. And it may present itself as being a very simple explanation of the theory of relativity, but don't be frustrated, because if you've never thought about this before, it's going to take a lot of thought. You're going to have to sit down and think and stop and really contemplate some of what you've read in order to grasp into some of these concepts. So we just scratched the surface, but hopefully it'll allow you to think, in a way that many people haven't considered about maybe time not being the constant, time being the thing that changes instead of something else, which most people would think that just time just goes by at a certain rate. So this will change the way you think of the world. It would change. It would just change the way that you view the universe if you're interested in getting that book. So I'll put the link in the description. Thank you as always for watching. Please like and subscribe, and We'll have probably something like this in the future. We may talk about whether or not the past still exists. Maybe something about a block universe. This is some interesting stuff, you know. But there's other videos we're probably going to do in the meantime. You know, Prof's got things he has to do also. So thank you for watching. Please like and subscribe, and we'll see you next time. Good boy, stay there, stay there. All right, so a little screen test. Okay. Go with